Hi, we will solve extra problems from chapters 21 through 24. The first example is that we have a rectangular charge distribution, and we would like to get the electric field at a distance z away from the surface. Okay, what is the electric field? We know the electric field should be obtained from some kind of stripes like that, and inside there is dq, and we say that the length is y and the thickness is dy, and inside there is dq. So we can write this expression: dq equals dq equals lambda times dy. Okay, instead of charge integration, we will go to the y integration. So electric field will be given as k times q over r squared. Don't forget. Now we have to specify what r is, what kind of q we have, and so on. So as you see, this stripe has a distance, okay, r, where the height is z, okay, and the electric field direction due to this dq is going to be this way, de, okay. But we know that because of the symmetry, this is, by the way, this is x direction, this is y direction, and this is z direction, okay. We know if you put these stripes to the other side, the electric field will be totally in this direction, so that only the projection onto the z-axis will be taken. So we have to consider dE times cosine theta. So this is dE cosine theta, what we are interested in, where this angle is theta there. This is also angle theta. So the other components, the perpendicular components, will cancel each other due to the symmetry. Okay. Now, r can be written, of course, in terms of z and y. Okay. For instance, tangent theta is equal to y over z. So this is an expression that we will use. So just keep that in mind. Now, this expression is correct, but for our dq we have de, and this is given by k dq divided by r squared. Okay, r squared. And now we have to also multiply this by cosine theta, so that electric field in z direction is just the integral dE times cosine theta. Okay, so now dE is k dq over r squared. Okay, but dq over, instead of q integration, we go to y integration, so that it's written as k lambda dy divided by r squared. Okay, r squared. Okay, now we would like to use this opportunity that y and z are related to each other, although z is not changing in this integration, because this is y integration, okay, and y integration, and we will go to theta integration from here. So y will be equal to z times tangent theta, okay, and then if we take the derivative with respect to theta, this expression will give you z over cosine square theta. So dy can be written as just z over cosine square theta, okay, times d theta. Now, if we also put r, since remember that cosine theta is equal to z over r, if we use all these expressions here, this is what we will get. Okay, we will get all the simplifications, and we will get just k lambda integral, okay, d theta, right? Cosine square theta, everything will cancel. We will get d theta, and then the angle will be from minus pi half to pi half, okay? And finally, this result will give you just sigma over 2 epsilon 0, okay? Where we use this sigma, okay, sigma times dy will be equal to just d lambda. Okay. Or instead of lambda, we are using sigma times L if the length is L. So there will be some L's here because, okay, the length of the stripe is this, and we can use, we can go from lambda to sigma, and basically this will be giving you just sigma over 2 epsilon 0. And now if you want to write this electric field in z direction, or just vectorally, electric field will be sigma over 2 epsilon 0 times k unit vectors from this expression. So don't forget, we went from the lambda to sigma. Okay, so this was the first example. The second example we would like to do is now, the second example is here. We have two charges, 2-point charges. One is minus q0, the other is minus 4q0, and we place a charge q in the middle at a distance x. It means that this is x equals 0, by the way. So the distance x, we just place charge q and find this is the distance between the two charges, q0 and 4q0 is L. Okay. Find the distance x at which force on q is 0. Don't forget, the force is always given by k, q1, q2 divided by the distance square. But now, let's draw the forces due to these charges. Since this is minus and plus, it will be attractive force between the two, so that it will be this way, okay? And we call this as Fq0. But for this one, the force will be this way, and F4Q0. This is the name I give. But, so we have to write the distances correctly, okay? And also the charges correctly. So Fq0, the force due to this Q0 is given by K times Q0 times Q. The two charges are Q0 and Q divided by the distance square, which is x squared, okay? So this is just the magnitude, and the direction is in negative x direction. But F4Q, however, is just K 4Q0 times Q divided by the length. But now this length, the length between Q and 4Q is L minus x, don't forget. So it will be the square of L minus x. So now we expect these two forces to be the same. Then we just equate this, okay? So that when we have Fq0 is equal to F4Q, okay? This gives you K and Q0 and Q's will cancel, so that 1 over x squared will be equal to 1 over L minus x squared. So now this is an equation. There is also 4 there. So there will be some 4, okay? There is a 4 here on the numerator of this L minus x squared. Okay, so now just we do cross multiplication. We get 4x squared, okay, will be equal to L minus x squared. So if we take the square root from both sides, we see that we get only one solution though. It just gives you 2x, okay, the square root of left-hand side, the square root of right-hand side is just L minus x, okay? So if you put this to the other side, we see that x equals L. But x equals L means that you just, this x is L means that Q is touching for Q0. This is not the case. This cannot be the case, okay? It's impossible. We need another solution. But don't forget, since this second order equation, you have to get 2 roots. So to get the second root, you have to do this. 4x squared left-hand side is equal to, now open this up. The square of L minus x is L squared minus 2LX, okay, minus 2LX plus x squared, okay? Now if you put this to the other side, put everything to the left-hand side, you get 3x squared, okay? Because you will subtract 1 from here, plus 2LX minus L squared is equal to 0. And this has roots as L over 3 and L. And we found L. but L over 3 is the one which we will use, so that x equals 0.33 L is the point at which force is equal to 0 on Q. So these two forces will be exactly equal to each other when we have 1/3 of the total distance away from this Q0. So this was the second example. Let's jump to the third one, okay, as quickly as possible. Okay, now, okay. Take some time to remove the table. Okay, in the third example, we have spherical shells, two spherical shells. But their surface charge distributions are given by sigma 1 and sigma 2. So sigma, don't forget, is equal to Q over A, and A being 4 pi r squared. This is the surface area of the sphere. So now sigma can be positive and negative depending on the charges given. Now the radii are given as R1 and R2, R1 and R2, and we would like to find the electric field everywhere. Of course, we assume that if the charges are positive, electric field is in the radial direction, okay? But if negative, in the radial direction, but directing the center, okay? So also outside there will be electric field, but inside there will be no electric field. When R is less than R1, if we use Gauss's law, Gauss's surface, okay, there will be no charge included, so that Q enclosed is 0, and we will have basically just EDA, okay, which gives you E times 4 pi r squared, because E is going to be constant for the spherical case. Right hand side, Q enclosed divided by epsilon 0. This was Gauss's law, remember? Okay. In our expression, right hand side, when R is less than R1, Q enclosed is 0, because there is no charge enclosed, because all the charges are on the surface of this inner sphere. So then we have electric field to be 0. E times 4 pi r squared will be equal to Q divided by 0, which is 0. So the only way that this expression to be 0 when electric field is 0. So E is 0 here. Actually, it's the case. We know already. We can directly say that this is Faraday's cage, by the way. So we can write this. This nice. What about R being between R2 and R1? Okay, R being between R2 and R1. In this case, we have to be able to write the enclosed charge very carefully. Okay, because now we have this case. Gauss's law, Gauss's surface now. Okay. Now we have this. So I'm just putting the arrows, which Gauss's surfaces we are using. For this region, Q enclosed is nothing but just due to this sigma 1 only, because there is no other charges. But Q is sigma times area. Okay. Sigma 1 times, okay, 4 pi R1 squared. You have to get R1 because greater than R1 there is nothing, okay, but less than R1 also there is nothing. All the charges are at R1, that's why you have to put R1 there. And now if we apply Gauss's law, left hand side will be equal to E times 4 pi R squared, which is equal to sigma 1 4 pi R1 squared divided by epsilon 0. So 4 pi's will cancel. Okay, 4 pi's will cancel, and we will have just electric field to be, so therefore electric field will be equal to sigma 1 R1 squared divided by epsilon 0 R squared. So this will go to the denominator of the right expression. So it's again similarly just Q divided by r square. Okay, K times Q over r square, where charge is written in terms of sigma. Okay, so what about the other region when r is greater than r2? When r is greater than r2, we have this Gaussian surface. Okay, here we go. Now we have this Gauss surface. So don't forget these arrows. Okay, when we have this, now we have two charges, Q1 and Q2. So that again, on the left-hand side, E 4 pi r squared will be equal to Q1 plus Q2 divided by epsilon 0. Okay, but Q1 and Q2 are written in terms of sigma times A. So it's equal to, the first one is sigma 1 times pi 4 pi r1 squared plus sigma 2 4 pi r2 squared divided by epsilon 0. Now when we divide this expression by 4 pi r squared, we solve the electric field. So electric field for this region will be simply given by 4 pi over 4 pi's will cancel, by the way. 4 pi's will cancel, and then when we have this cancellation, all we are left with on the numerator will be sigma 1 r1 squared plus sigma 2 r2 squared. Okay, and the denominator will be just epsilon 0 times r squared. So this is the expression we have. Okay, so we will have just this electric field to be given by this expression. So I will just put this in the circle. So as you see, in the first region, we have zero electric field. In the second region, we have electric field given by this expression, which becomes in the radial direction, but either away from the center or towards the center, depending on the charge being positive or negative here. And there is no way that the electric field is zero, but there is a way that electric field may be zero outside here. So outside, it is possible that electric field is zero. So there is a point at which electric field is zero. So how can we find that point? So what do we get? What kind of condition do we have in order to have this electric field to be zero? But we have to use this expression. So when it is zero equals, okay, sigma 1 r1 squared plus sigma 2 r2 squared divided by epsilon 0 r squared, a special r, of course, is equal to 0. Then the denominator is not important, but the top is to be 0. So sigma 1 r1 squared must be equal to minus sigma 2 r2 squared, or sigma 1 over sigma 2 should be equal to minus r2 squared over r1 squared. Now let's do this. Suppose that sigma 1 is equal to just q0 over a. Okay, but we have to write these areas as 4 pi r squared, r1 squared, and sigma 2 is again, let's say, minus 2q0 divided by 4 pi r2 squared. In this case, when you put these expressions here, okay, sigma 1 over sigma 2 will give you q0 divided by 4 pi r1 squared divided by 2q0 divided by 4 pi r2 squared with a minus sign. Of course, this minus sign goes to top. The right hand side is minus r2 squared divided by r1 squared. Now, as you see, 4 pi's will cancel, q0's will cancel. Okay, so what we did is that we put plus q0 here and minus 2q0 there. So the charge on the outer surface is twice as much as the inner one. Okay, but now we have just all these cancellations done. So R1, so right hand side also has a minus sign, so the minus signs also cancelled. So we have 1 over R1 squared divided by 2 over R2 squared, which is equal to R2 squared over R1 squared. Okay, now so So what do we have? What we have is that if we get the square roots of both sides, we get 1 over square root of 2, okay, R2 over R1 will be equal to, okay, R2 over R1, okay? So basically, in this case, we will have the ratios to be equal to each other, but it is only possible when it is multiplied by 1 over square root of 2. So basically, this expression gives you just the electric field, which is totally zero when this condition is satisfied. Okay, so outside it is possible that we have this electric field. Now, the third example, the fourth example we would like to solve, okay, is the fourth example is given by the cylinders. So we have now an inside cylinder at which the charges are distributed uniformly. Technologically, it's not easy, but it can be done. So outside, we also have another region where we have exactly the same case. Okay, here also the charges are distributed homogeneously. Okay, we have shell outside and solid cylinder inside. Okay, like that. And now let's give the names to the radii. The first one is R1. The second radius is R2. And the third radius is R3. So we would like to find the electric fields because of these kind of charge distributions, okay? But now since it's the volumetric charge distribution, okay, we will use, okay, the Gaussian surface, okay, we will use Gauss's law. Let's write it down. E dot dA, which is equal to just Q enclosed divided by epsilon 0, okay? But now we have to specify the Gauss's law. For instance, if we consider the Gauss's law inside, okay, inside here, okay, inside this region, where we have the length L, this length is not important. The length of this Gaussian surface is L. Now the electric flux from the side surfaces, left surface and the right surface will be 0. So electric flux on right and left surface equal to 0 because the electric field is totally perpendicular to the surface area normals. For instance, the right surface area normal is this way, okay? But the electric field is from the center that way, so that there is 90 degrees between them. And this dot product gives you 0 because there is no projection of electric field onto this area vector. So no contribution from the flux, but only the size on the left and right surfaces, but the side surface will just have this. But the side surface area, so if you look at here, this is 2 pi RL, which is circumference. Okay, 2 pi RL, circumference of this circle, and L is the length of this cylinder shell, so that this area will be just area is equal to 2 pi R times L. So this is 2 pi R, and if it is multiplied by L, you get 2 pi RL. So on the left-hand side, we have just E times 2 pi RL always, okay? Now, for Q enclosed here, okay, we have to be careful because it's just a portion of total charge. Now, we know that rho, which is volumetric charge density, is Q over V, volume, okay? But now, Q enclosed will be equal to just simply Q enclosed will be equal to rho, which is constant homogeneous charge distribution. Sometimes this also changes with R. We give this as an extra example. So rho times volume, but the volume, for the volume, you have to write pi R squared times L. So this is the volume of this cylinder. So volume of the cylinder is, if the radius R, of course, is just pi R squared, the base area, times height, Okay, that's why you have to use this expression here. This is the volume times the charge density. This is what we have to write down here. So it's just rho times pi r square L divided by this epsilon zero. Don't forget this Q epsilon zero. Now what happens? Pi's will cancel, and one of the r's will cancel, and l's will cancel, and then we will have electric field to be given by rho times r over 2 epsilon zero. It's a linear dependence on r. Inside this cylindrical wire, solid wire, by the way, not metal. It cannot be a metal. Okay, it can be only a non-conductor, because when we have metal, all the charges will suddenly move to the outer surface. This is not possible to have this kind of distribution. So these parts cannot be conductors. But some nanoparticles or some charges distributed inside. Don't forget. Because for the conductors, don't forget, the charges always move on to the surface. Even from the cables that you are using at home, the charges are always flowing on the surface, not inside the wire. Okay, when we have now between R1, R2 and R1, it means that we are now in this region here, this region. So the charge enclosed is nothing but just simply Q enclosed is just the charge coming from inside, which is just rho times total, rho times V total, V total. So what is that? Rho times 4 over 3, okay. Since this is not the sphere, it's just a cylinder, we have to use, for the volume, we have to use pi r square L. So pi r square, but r is, for r, we have to use r1 because we have to consider everything times L. So Q enclosed is given by this expression. Okay, so left-hand side is always E times 2 pi RL. Right-hand side now is rho times pi R1 square L divided by epsilon zero. Don't forget, for Q enclosed, we have to use R1 square because now we are enclosing the whole. So this is this Gaussian surface. Now the Gaussian surface we consider, okay, is this case. Okay, it includes R1 as you see. Okay, so now what happens is that pi's will cancel, L's of course will cancel, so the length is not important as you see. So the electric field will be given by, okay, rho R1 square over 2 epsilon zero times 1 over R. So it's inversely related to R. Here it's increasing linearly with R, but inside this region, okay, it's reducing by R. Okay, now what about the region between R2 and R3? Okay, when R is between R3 and R2, now Q enclosed, first the total thing, just like we have here, rho times pi R1 square L, but plus now we have this, you have to be careful now. You have to get the total surface area of this shaded region. Okay. Now this region, I just put an arrow here. This region, right there. So what is the surface area of this thing? It's obviously, if you just call the Gaussian length, always Gaussian surface length as R, it's R square minus, okay, pi times R, pi times small r square minus R2 square. So it's just the surface area or this area of this stripe. And if you multiply by L, it's the volume. It's the volume. Now, if you multiply by rho, it gives you the total charge within this shaded region. So this is the total charge. So this is the charge that we have to use, okay? So I'm removing this expression here not to confuse you. Okay, now this is the total charge for this stripe shaded region, but also we have another charge which is coming from inside, again, rho pi R1 square L, just like we have done earlier, okay? This is edit, that's why I'm just writing Q enclosed here. So this is inner part plus outer part, but just the difference between the radii. You have to be careful because it's just this little volume that we are considering. Of course, these surface areas are multiplied by L to get the volume. So this is Q enclosed. If this is Q enclosed, then simply we have E times 2 pi RL as before here will be equal to this charge, which is Q enclosed, divided by epsilon 0. So now how can we write this as simple as possible? So we have rho there, okay, L there, and pi we have to, okay, R squared plus R1 square minus R2 square. So it's the simplest expression we have, divided by epsilon 0. Now L's will cancel, pi's will cancel, and electric field will be given as rho over 2 epsilon 0, okay, R squared plus R1 square minus R2 square, everything divided by just the R on the left-hand side coming here. So this is the electric field expression between R2 and R3 here, okay. So this is region 1, this is region 2, and this is region 3. Now outside, region 4. So this is region 2. Region 1 I'm writing here, E equals rho R over 2 epsilon 0. This is region 1. This is region 2, 3. So let's keep these expressions here because we will do the graphing thing. So now I will just remove this part and show you that now our Gaussian surface is outside. Just this one. Okay, new Gaussian surface. When R is greater than R3. Now, this Gaussian surface includes, okay, Gaussian surface includes all charges, Q1 and Q2. What are they? It's just the volumetric charge density times the volume of this thing. So what is that? Q1, so Q enclosed is just the sum of Q1 and Q2, which is given as rho times, okay, pi R1 square times length, okay, just this volume of this thing, inner cable, plus rho pi R2 square now, R3 square minus R2 square, Don't forget, the total surface area of this thing is, you have to consider 2 radii, outer radius is R3, inner radius is R2, so that you have to get the area, you get pi R3 square minus pi R2 square. Okay, this is what we have there. So now electric field then will be given as, if you divide this by 2 pi R, okay, it will be given by, pi's will cancel, and then we have epsilon 0 over 2 epsilon 0, rho over 2 epsilon 0, pi's got cancelled, and L's also got cancelled. We have now, R is here, okay, R1 square plus R3 square minus R2 square, divided by R. Again, 1 over R dependence. This is region 4. Region 4. As you see, region 4 included all these charges, but the second charge is included in this small area, which is defined as R3 square minus R2 square pi, okay? That is the reason that we wrote it this way. So now I would like to do the graphing business, okay? So how can we graph these function as a function of R? We have to put R1 now, R2, R3, and outside. This is the electric field. So when you draw a graphing system, okay, graph axis, you have to put the names of these things. Y-axis, we have electric field. In the x-axis, we have R. So you have to, the first thing we have to do is just place these things. It's important. So inside, in region 1, the linear dependence with R. So it will increase like that. Okay, it will reach some value where this R is replaced by R1, rho times R1 over 2 epsilon 0, rho times R1 over 2 epsilon 0. And then after that, in the second region, it will drop like 1 over R, okay, like that. It will drop like this, and then reach down to, when you put R2 there, R1 square over R2. So this will be giving you, this expression is exactly the same thing where this R is replaced by R2. So rho R1 square divided by 2 epsilon 0 R2. 2 epsilon 0 R2. Okay, now is this the case for region 3? Yes, because when you replace R by R2, at this point, this cancels each other, okay? And then R1 square over R2, exactly the same expression we have. Good. But from now on, we have to use this expression for region 3, which seems to be an increasing function because there is R square on the top and R on the bottom. It looks like if these two expressions were not there, it would be a linear dependence or R, but since this have, okay, there will be some kind of curvature in this increase. It's not going to be a linear increase. Okay, so if you graph this, it will be increasing like that, you know, not linearly as we have here in the first region. Okay, so it will increase to a maximum value. So what is that? When R is replaced by R3, then we have this. So now this expression here is just this electric field, rho over 2 epsilon 0 times R3 squared plus R1 squared minus R2 squared. Okay, minus R2 squared divided by R, but R is R3. So this is the electric field at this point. And then from now on, we have region 4. Again, it's 1 over R dependence. So it goes like that again. Okay, following the same kind of slope, of course, like that. Okay. So the slopes of this region and this region will be exactly the same because it will be 1 over R dependence. So this is the electric field graph within all the regions. Good. Now let's jump to the other example. Okay. Now the fifth example we are solving is given by this simple thing. Okay, we have now x and y axis. This is y axis, this is x axis. We place a negative charge here, minus q. And q is given as, okay, q is given as 3.8 microcoulomb. Okay, the charge is given. And we would like to find the potential at point A and the potential at point B, where this distance is 70 centimeters and this is 80 centimeters. Okay, 80 centimeters. So we would like to find what is VA, what is VB, so that we can get delta V, VA minus VB. Also, what is the electric field at A and what is the electric field at B? So we would like to find the potentials and the electric fields. Let's write the expressions for the potential and an electric field. Electric field is KQ over R squared, but the potential is KQ over R. Don't forget, we will use these expressions. Because we have now only 1 point charge, so the potential at point A is just K, which is 9 times 10 to the 9, times the charge, which is 3.8 times 10 to the minus 6, micro is minus 6, divided by the distance, which is 0.7. So when we do this, we see that the potentials, of course, will be all negative because the charge is negative. So put a minus sign. Minus, okay, the first voltage or potential will be 4.89 times 10 to the 4, okay, volts, of course. The potential energy is joules, but the potential is volts. VA is exactly the same numbers we have, 3.8 times 10 to the minus 6, but now instead of divided by 0.7, we will have 0.8, and it will be given as, again, of course, we have to use the minus sign again. It will be just 4.28. Now it will be smaller slightly, times 10 to the 4 volts. What about the electric field? First of all, we have to find the direction of the electric fields because it's a vectoral thing. Because this is negative, the electric field will be this way, okay? And this way, and this way, and that way. So basically, for the electric field in A, at point A, it will be in negative y direction, minus y direction. But here, it will in plus x direction. Okay, the electric field will be plus. So we just forget the plus and minus signs. We know the directions, we get the magnitudes. EA will be given as just the same expression, but we have to get the square of this on the denominator. 9 times 10 to 9 times 3.8 times 10 to the minus 6 divided by 0.7 square. So the result is 6.98 times 10 to the 4. Okay, it got a little bit larger than this one because it's the square of a number less than 1, so it makes this expression slightly bigger. Okay, so it Newton per coulomb or volt per meter, right? Electric field dimension. So EB is also the same thing, and it gives you 5.34 times 10 to the 4 Newton per coulomb. So if you coulomb, if you write the electric field as in vector form, minus 6.98 times 10 to the 4 J, because it's in negative J direction, but EB is in positive X direction, so it's 5.34 times 10 to the 4 I. Okay. Now we can get the VB. VA minus VB, so this was VA and this was VB, by the way, or get the electric fields, and okay, so electric field is given by that in minus J direction and positive X direction. So this was the extra fifth problem, and maybe one more example if we can solve. Let's see if we can solve it or not. We don't have enough time to solve this, but we will solve the rest of the examples on Wednesday, guys. Okay? Now I stop recording.